So far in our probability unit, we've looked at problems involving not and or. In this video, we'll look at problems with and at least one. Let's start by looking at an experiment where we toss a coin twice. What's the probability of getting heads both times? Well, on the first toss, there's heads and tails, so we would expect to get heads half of the time. To get it both times, you got to get it the first time. So out of that half that we get it the first time, then we expect on the second toss another half of that original half to come out heads the second time. So half of a half would be the fraction that we expect to be heads both times. To find half of half, we'd have to multiply a half times a half, which means a fourth of the time we'd get heads both times. Note that to get a head both times, that means we would have to get heads on the first time and heads on the second time. This is an and problem, even though I don't see the word and. Sometimes and problems don't actually contain the word and, but rather a word like both or all or neither, some word that implies and. So to find the probability of getting heads the first time and the second time, we multiplied. That's the rule for and problems. The probability of two events A and B both occurring would be found by multiplying the probability of A times the probability of B. We'll talk in a moment about this word, the idea of independent events. Example 1. We have a spinner. The pointer on the spinner is spun twice. Find the probability that will land on the 3 and then any odd number. Well, the spaces on the spinner go 0 through 9. That makes 10 spaces on the spinner. So the denominators of our fraction will be 10. For number 1, since we want the probability of an and event, we'll be multiplying probabilities together. Well, the probability of spinning a 3, only one 3 on the dial, so that would be 1 out of 10, times the probability of any odd number. On the spinner, there's 1, 3, 5, 7, 9, which would be 5 odd numbers, so probability is 5 out of 10. Multiply them together, multiply the numerators and denominators, and we get 5 out of 100, which reduces to 1 over 20. For number 2, we want to get a number other than 3 each time. Here's another example where I don't see the word and, but it's implied because I would need a number other than 3 the first time and a number other than 3 the second time to get it each time. The probability that I get a number other than 3 would be 9 out of 10. Since we're only excluding one number, it leaves us with 9 out of 10. So we'll multiply 9/10 times, second time is also 9/10, which gives us 81 over 100, which is already reduced. Each spin of the pointer is called an independent event. Because no spin affects the results of any other spin. Spinners and dice are always independent events. Drawing cards can be independent events or not. It depends on how we draw them. Example 2 asks if we draw 3 cards from a deck, what is the probability that 3 red cards are chosen? Well, there's 2 different ways we can draw the cards. Part A asks with replacement. That means that after each draw, the card is returned to the deck and the deck is shuffled. Or without replacement means when you draw the cards, you'll leave them out of the deck. That's the more typical way that we draw cards, but they can be done with replacement. Well, if we want all 3 cards to be red, that would mean we would need a red on the first draw, and a red on the second draw, and a red on the third draw. So again, I don't see and, but this is an and problem, which means we'll be multiplying 3 fractions together. On the first draw, regardless of part A or B, we'll be drawing from the full deck. So the probability of getting a red on the first draw, out of the 52 cards, we have 26 red cards, so 26 out of 52. For the second draw in part A, we're putting the first card back in and reshuffling. So we're back to the full deck again. So the probability of red on the second draw is still 26 out of 52. Third draw, same idea. I'm back to the full deck, so probability red on the third is again 26 out of 52. It might be easier to reduce each fraction before we multiply, since 26 out of 52 is 1/2. So we'll get 1/2 times 1/2 times 1/2, which equals 1/8. Or if we want to convert to decimal form, that would be 1 divided by 8, which is 0.125. For part B, on the first draw, we have the full deck. So probability that we get a red on the first draw is, again, 26 out of 52. But this time, we'll keep that first card out of the deck. Now, if we didn't get a red on this first time, we've already failed. So we're going to assume that we did get a red the first time. So for the second draw, think about what remains in the deck with 1 red card gone. How many red cards are left? How many total cards are left? Well, 1 red card has been removed, so now instead of 26, there are only 25 red cards. And instead of 52 total, there are only 51 total cards. So the probability of red on the second draw is now 25 out of 51. For the third draw, yet 1 more red card has been removed. So now we're down by 1. We only have 24 red cards and 50 total cards left. Probability of red on the third draw is 24 out of 50. Multiply the fractions. I'll reduce the first fraction to 1/2 since that's an easy one, but I don't want to bother reducing the others since I'll be leaving my answer in decimal form anyway. So multiplying the numerators, 1 times 25 times 24, that's 600. And the denominators, 2 times 51 times 50 is 5100. And now divide 600 by 5100 on a calculator. Which gives us 0.117647 . Or rounding that to 3 decimal places, we'd go to 0.118. Since the 4th digit, 6, is 5 or more, this will go up to 118. The answer to part B is slightly less than the answer to part A, because if we're going to remove the cards, it becomes less likely that we'll get a red. since we keep removing the reds. We've been talking about independence. Well, in part B, the events are not independent. Independent events means the probability of one does not affect the other, like cards or dice, but if you're going to remove cards, you are affecting the probability as it goes along, so this is not independent. Well, our original multiplication rule here says it was for independent events. So does the multiplication rule still apply? Well, yes, it does. We still multiplied. But we have to adjust the fractions because we assume as we go along that the card we wanted previously has already been removed. Notice that in all these problems we are doing more than one trial. We spun the spinner twice. We drew 3 cards from a deck. This is a hallmark of AND problems. By contrast, OR problems often involve only one trial. Roll a die, or the dice once. Draw 1 card from a deck. Also notice in AND problems that the number of trials is the number of fractions that are multiplied. So if we spin the spinner twice, we multiply 2 fractions together. If we draw 3 cards, we multiply 3 fractions together. Example 3. A cooler of 30 sodas has 12 Pepsis, 11 Cokes, and 7 Sprites. If Kim chooses 4 sodas randomly without replacement, what is the probability that, number 3, they will all be Cokes? Since Kim is choosing 4 sodas, we'll have 4 fractions to multiply together. Notice again that we have to infer that this is an AND problem from the word all. If all will be Cokes, that means it's Coke on the first, and first on the second, and the third, and the fourth draws. This example does specify without replacement, but even if it didn't, I would assume that in problems where we're removing items from a box, a cooler, a jar, etc. There are 11 Cokes and 30 sodas to start with, so the probability of Coke on the first draw will be 11 out of 30. In each subsequent draw, 1 Coke will have been removed, so a Coke on the second, we take each number down by 1 and make it 10 out of 29. On the third, 1 less again, so 9 out of 28. And the fourth draw, 8 out of, just corrected a mistake there, is 9 out of 28. And now the fourth draw is 8 out of 27. And we'll multiply these 4 fractions. Multiply the numerators, that's 7920, the denominators, 657,720. So multiply the numerators, 11 times 10 times 9 times 8, that's 7920. And then multiply the denominators, 30 times 29 times 28 times 27. That's 657,720. And then divide that on a calculator. 7920 divided by 657,720 gives us 0.01204, and rounded to 3 decimal places it would be 0.012. Example 4 is the same situation, choosing 4 sodas from this cooler. On number 4, we want the probability that the first 2 will be Pepsis, the third will be a Coke, and the fourth a Sprite. Well, on the first draw, we're looking for a Pepsi. There are 12 Pepsis and 30 sodas to start, so the probability of Pepsi on the first will be 12 out of 30. Then we want the second to also be Pepsi, but 1 Pepsi is removed, so now there's only 11 Pepsis and 29 sodas, so the second fraction is 11 out of 29. Now for the third draw, we want a Coke. The first 2 times we removed a Pepsi, so still we have all the Cokes in there. There's still all 11 Cokes in the cooler. So we'll have 11 in the numerator, but since we did still remove another soda, the total will always go down, so it'll be 11 out of 1 less, 28. Fourth draw, we want a Sprite. So all 7 Sprites are still in there, but 1 soda has been removed, so only 27 remain. So it's going to be 7 out of 27 total that remain. Multiply the numerators and the denominators together. Numerators 12 times 11 times 11 times 7 is 10,164. And then the denominators, 30 times 29 times 28 times 27 gives us 657, 720. Oh, I guess I should have known that, because look back at part A, that was the denominator there, and it was the same one. So often if you have 2 problems on the same situation, that was kind of a waste of time. I didn't need to do that. You can just look back and see what it was here. So it's 10,164 over this denominator, 65,720. So dividing the top, 10,164, divided by the bottom, 657, 720, we get 0.01545, rounded to 3 decimal places is just 0.015. Next example. 3 cards are drawn from a deck without replacement. What is the probability that none of the cards are hearts? None can be a tricky concept. To draw 3 cards and have none of them be hearts, I have to not draw a heart on the first draw, and not a heart on the second draw, and not a heart on the third draw. Or another way to say this is that I need all 3 draws to be not hearts, or what I need to draw are non-hearts. Well, there are 13 hearts in the deck, so all the rest of them, which would be 52 minus 13 would be 39 cards in the deck, are non-hearts. I want to only draw non-hearts. So we can rephrase this, none of the cards are hearts, to say we want all of the cards to be non-hearts. And that way I know I want to draw from the set of 39 non-hearts. So none are hearts would be all are non-hearts. Well, we said there's 39 non-hearts. We're drawing 3 cards. So on the first draw, there's 39 non-hearts out of 52 cards in the deck. So probability of a non-heart on the first draw would be 39 out of 52. I assume I've removed one of the non-hearts. So now for my second draw, There's no longer 39 non-hearts. There's 38 non-hearts and 51 cards total. So 38 out of 51. Third draw, 37 non-hearts out of 50 cards left. Multiply the numerators. We get 54, 8, 34. Denominators, 52, 51, and 50. $132, 600. Divide on our calculator. Top number, 54, 8, 34. Divided by the bottom number, 132, 600. And that gives us 0.413529, or rounded to 3 decimal places, it would go up to 0.414. In example 6, we want the probability that at least one of the cards is a heart. What does at least one mean? Well, at least one could mean out of the 3 cards that either 1 or 2 or 3 are hearts. It's complicated to find the probability of all the possible ways to get at least one. So it's actually easier to figure out how we would fail to get at least one. Well, when would we fail? If we get any, we have at least one, so we would fail if we don't get any. So we fail if we get no hearts, or none of them are hearts. At least one and none are complements of each other, because we'll always have exactly one of those situations. Either at least one is a heart or none is a heart. So at least one is the complement of none. Our formula for complement is to subtract from 1. So the probability of at least one is going to be 1 minus the probability of none. And that's a formula. We actually already did this part up in number 5. So in number 6, where we want the probability that at least one of the cards is a heart, the probability of at least one is 1 minus the probability of none. So for number 6, we just need to subtract, using the formula, 1 minus our answer to number 5, which was 0.414. So 1 minus 0.414 which equals 0.586. Finding the probability of at least one is always a two-step problem. You first have to find the probability of none, and then subtract from 1 to find the probability of at least one. In number 6, we happened to have just found the probability of none in number 5. If we hadn't, we still would have had to do that step first before we could find the probability of at least one.